Have you ever wondered how things move? Not just wheels turning or gears spinning, but the real, straight line pushing and pulling that makes our world work. The force that lifts a car in a garage adjusts your desk to the perfect height, or even helps a pilot steer a massive airplane. The answer, my friends, is one of my favorite unsung heroes of engineering, the linear actuator. It's a beautifully simple device with a profoundly important job. A linear actuator is anything that creates motion in a straight line. It's the muscle behind the machine. And trust me, once you start looking for them, you'll see these incredible gadgets absolutely everywhere, hiding in plain sight. Think of it like this. A motor is great at spinning things around. That's called rotary motion. But what if you don't want to spin? You need to push something forward, pull it back, lift it up, or press it down. You need to convert that spinning energy into a straight line. Cut to diagram. Motor turns a screw, which causes a rod to move in and out in a straight line. That's the core job of a linear actuator. It's the bridge between a spinning motor and a precise, powerful push. It's the difference between a fan blade just spinning in circles and a robotic arm reaching out to grab something with pinpoint accuracy. So, how does a linear actuator actually turn a simple spin into a powerful push? The most common way, especially in electric actuators, is pure mechanical genius: the lead screw. Imagine a regular bolt. Imagine a nut. If you hold the nut still and turn the bolt moves forward or backward, right? Now make that bolt really, really long. That's your lead screw. Attach a motor to spin that screw. Put a nut on it that can't spin, but is attached to a rod. As the motor turns the screw, the nut travels up and down, pushing or pulling the rod. It's that simple. The screw gives you a huge mechanical advantage. A small, fast-spinning motor can generate an incredible pushing force. It's like using a car jack to lift a 2-ton vehicle with just your arm. You're trading speed for power. The motor might spin hundreds of times, while the rod moves only a few inches. That trade-off lets small devices do huge work. Think of a ramp. Pushing a box up a wall is hard. Pushing it up a long, gentle ramp is easier. A screw is a ramp wrapped around a cylinder. Each turn moves you a little way up that ramp. That's why you get fine control. You can turn the screw a tiny bit for very slow, precise motion. All right, let's meet the main players in the actuator world. First up, we have the brains of the bunch, the electric linear actuator. This is the type we talked about with the lead screw. They run on electricity, using a motor to drive the mechanism. These are the darlings of the modern era because they are incredibly precise, clean, and easy to control with computers. Think about an adjustable standing desk. You press a button, and a small electric motor in each leg turns a screw, lifting the entire desk smoothly and quietly to a preset height. They don't need messy fluids or noisy compressors. Next, we have the speed demon, the pneumatic linear actuator. These guys run on compressed air. The setup is simple: a cylinder, a piston inside it, and a couple of air hoses. You pump high-pressure air into one side of the cylinder, and whoosh! The piston shoots to the other end with incredible speed. To move it back, you just pump air into the other side. Because they are so simple and fast, you see them all over factory assembly lines. They're perfect for quick, repetitive tasks like stamping a label, opening a gate, or ejecting a finished part. They are the sprinters of the actuator world. Finally, we have the heavyweight champion, the hydraulic linear actuator. These are the ones you call when you need to move something really heavy. Hydraulics use a pressurized, incompressible fluid. Push in one place, get force out somewhere else with almost no loss. Now that you know what to look for, you'll start seeing linear actuators in the most unexpected places. It's one of my favorite games to play. Take a modern farm, for example. The giant combine harvesters that gather our food are loaded with them. Hydraulic actuators lift and lower the massive cutting header, while electric actuators make micro adjustments to sieves and sorters inside. It's a symphony of controlled linear motion, enabling a few people to harvest thousands of acres efficiently. These machines are basically giant, specialized robots on wheels. Here's a fun fact: the rumble or haptic feedback in a game controller. Some advanced controllers and simulators use tiny, high-speed linear actuators. They're called linear resonant actuators, or LRAs. They vibrate back and forth at specific frequencies. This creates more nuanced, detailed feedback than a simple spinning weight. That kick or road texture you feel? A tiny linear actuator translates code into motion. Think about the entertainment industry. How do they make scenery appear, fly in, or transform? You guessed it, a network of linear actuators. Silent stagehands, precisely cued by computer. From theme park characters to blockbuster dinosaurs, linear actuators bring creations to life. From your car's automatic trunk to a surgical robot's complex dance, linear actuators are vital. They are the bridge between our digital commands and physical reality.